Hello, this is question 4 from the 2015 MAT. A circle A passes through those 2 points. It's got centre M, H, radius R. Determine M and write R in terms of H. Right, little sketch just to lay the land then on this. Makes it so much easier to visualise. So we're going through -1, we're going through 1. That's not going to define a circle because, of course, we could draw any number of circles through that. We need a third point to fix it. But the way that I've drawn it, I'm going to have to go this way. I haven't got enough space to draw upwards. So we could have that circle, but of course we could shift it further and further up until we actually had a centre. Yeah, m's going to be 0, isn't it? We could have the centre of the circle at the origin, and then we could move that centre up or down the y-axis. So we've got that m is 0. I suppose we should give a little bit of justification for that. We've got the y-axis is a perpendicular bisector of a chord. So let's go with that then. So we can say we've got a horizontal chord from -1, 0 to 1, 0. Therefore, the bisector is going to be vertical. We'll have a vertical bisector, which is the y-axis, will go through the center, passes through center. So that is why we're going to have that m is equal to 0. It's another symmetry argument, essentially. And we do like a symmetry argument when there's a geometry question. So that's given us what m is. So we know that the center is on the y-axis, and it's going to be, well, in this case, it's at h. Okay, h is going to be negative in this case. So, but I specified it as being h, so we can easily work out the radius then. So the radius squared is going to be h squared plus 1 squared. R is the square root of h squared plus 1. Right. Part 2. Given a third point, x0, y0, y0 is not equal to 0. So it can't duplicate one of the existing points, and we certainly can't have 3 points on the x-axis for the same circle. Then, I've lost where I'm reading now. Given a third point, y is not show there's a unique circle passing through these 3 points. So we want a unique circle, so we want to fix the center, is what we're trying to do. We've already fixed m, so we want to try and fix h. We want to have something that is going to pin h down. Okay, so let's go to our equation of a circle on this then. So we've got that m is 0, so it's just going to be x squared plus y minus h squared is r squared. We've got r squared, that's h squared plus 1. So we've only got h's in this. So if we can make h the subject and show that it is fixed for x0, y0, then we're sorted, aren't we? So let's put x0, y0 in, and I'll expand out that bracket. So x0 squared plus y0 squared minus 2hy0 plus h squared, so they're going to go away, is h squared plus 1. Cancel those, make this single h the subject, and we're done, aren't we? So h will be equal to, what we've got, x0 squared plus y0 squared minus 1 divided by 2y0. So we have got a fixed h along with our fixed m. That was nice, I like that. Part 3, we've got a bit to read before we get into part 3. For the remainder of the question, we consider 3 circles A, B, C, each passing through those points. Okay, each circle is cut into regions by the other 2 circles. For a group of 3 circles, we will say the lopsidedness of a circle is the fraction of the full area of the circle taken by its largest region. Okay, that's something to struggle to visualize, but maybe we'll be drawing a picture, I'd imagine, in the next bit anyway. Let circle A pass through that, B through that, C through that. What is the lopsidedness of circle A? Right, okay, I'm going to draw a picture in the big space on the right. So let's do some, so A is also going through, let's do some working out over here, 1, 2. B is going through 0, 1. And C is going through 0, minus 4. So what do we know then about, we know all of them have got m being 0. So let's get h for each one of these then. So that means A is going to have a centre at 0, and then h we can put into this thing over here. So we're going to have well, the ones will cancel, so we'll have 4 divided by 4. So that's going to be at 0, 1 for a centre. And the radius is going to be equal to, what am I doing? H squared. So 1 squared plus 1 root 2 is our radius. For B, that's just going to be a unit circle, isn't it? Because it's going through all these ones. So the centre is going to be at 0, 0 for B. So that's going to have centre 0, 0, radius 1. This one then is going to have a centre at 0. What have we got? So 0, 0, so we've got 16 minus 1, so 15 over minus 8. Okay, so we've got a slightly annoying one. And then we've got a radius, which, okay, we'll come back to if we have to do it. It's not like it's hard to work out, but it's just going to be a really annoying number. Right, well, let's draw some of this out then and then see what we can work out in terms of lopsidedness. I don't want to draw too big a picture here. So there's our axis, y-axis, that everything's lying on. Then we've got this. So we've got B is a unit circle. So okay, let's draw that in moderately big. Just hope I haven't picked a bad size to start on. So that's B. That's this one sorted. Then we got another one which has got a centre at 0, 1. All right, so it's got a centre here. It's got a radius of root 2. So it's going to go down there, and we know it goes, everything's going through these points. So let's do this in a different colour. Let's do that one in blue, which is going to go round there and round there. And this is the one we're interested in, isn't it? The lopsidedness of A. So clearly the biggest region is we're looking at this bit up the top here, you know, all of this stuff up here. And then C is going through minus 15 over 8. So that's outside of this. It's going to be down here somewhere is the centre. It's also passing through there and there. So yeah, that's not affecting anything in terms of the calculation. So we can just ignore C in order to work out what's going on here. So we need to work out then the area, the area of this, and then take it as a fraction of the whole thing. So right, let's start off then. Area of B in totality is, so pi r squared, so we've got 2 pi. Then what do we have to do? So we have to remove, oh wowzers, right, okay, so we've got a slightly annoying bit. We're going to have to split this up into lots of bits, aren't we? So we're removing this, we're removing half of circle B, and then we need to add on this bit, and also take off that bit, I mean, so as in add on to the bit we're taking off. So we've got half of circle B minus half, yes. What one am I doing? Oh, this is area of A, not B. Right, okay, that's what's confused me, yes. Area of A, this is what we're trying to work out. We have to take away half of area of B. So that takes off a big chunk, and we're just left with this little bit down here, all of this bit below the x-axis. So half of the area of B is pi over 2. So we have to take that off. Then we have to take off this, which we're going to have to do by taking off a sector and then adding the triangle on. So we need to take off the sector and add the triangle, because otherwise we would have taken off the triangle twice. That's 1, that's 1. So the triangle is going to have area 1 all in all, because essentially that's going to be a square, and it's split in half and flipped over. So the area of that is 1. The area of the sector, that's going to be 45 degrees, so that'd be 90 degrees. So we're taking off a quarter of the overall circle, which is another pi over 2. Okay, so we've got all of that. So the area, the biggest region, is going to be 2 pi minus pi over 2 minus pi over 2 gives us pi, and then we add 1, pi plus 1. Now we need that to be a fraction to give us the lopsidedness. So the lopsidedness, let's call it L of A, is going to be equal to pi plus 1 divided by 2 pi. That was nice. That was a fun exercise. Right, new sheet. Okay, so last part, part 4. Let P be greater than 0. Now let A pass through 1, 2P, B pass through 0, 1. So B hasn't changed. That's still the same bit. C pass through minus 1, minus 2P. So it's the opposite of A. Show that the value of P minimizing the lopsidedness of B satisfies that equation. Note that tan minor of 1x is sometimes written as arctan. Right, so that's just in case people use different notation. Right, well, we can do a similar thing then for A, B, and C just to see what's going on. Well, we know about B because B, that was saying, well, we've got the center at 0, 0, we've got a radius equal to 1. So we did add that on the previous one. So A is going through 1, 2P. So that means that our H is going to be, that was squaring these, adding them, taking 1 off, which will get rid of the x squared, and then divided by 2y, wouldn't it? So it will be 4p squared divided by 4p. So that's going to be at p. C is minus 1 minus 2p. So we'll get minus p for that, won't we? Because it will be the same when we square them, but we'll have a minus when we divide by the 2y. Then we've got r was the square root of h squared plus 1. So, okay, fine. That's just coming out as, well, square root of p squared plus 1. So let's just put p in there instead. We'll have the same thing here, won't we? R will be the square root of p squared plus 1. Okay, so let's do a little sketch then. Y-axis, x-axis, that's our B going in the middle between 0 and 1. And then we're going to have A up this end, which will go through here and round. That's at P. And then we'll have C opposite going through there and round. And we want to minimize the lopsidedness of B. So we want to have the smallest, largest area. So we've got 3 possible areas then, 1, 2, 3. So we're going to want to split it evenly then, aren't we? So we will minimize lopsidedness of B when 1 equals 2 equals 3 in terms of area. And the area of the circle is pi r squared, which is pi. So we want that to equal pi over 3. Okay, so let's pick one of these regions, which is going to be the easiest one to calculate. It's got to be 2, isn't it? 2 is going to be by far the easiest one to do, because we can take, if we take this sector here and then take off the triangle, then that will give us half of 2. So we're saying that pi over 6, that's half of area 2, has got to be equal to the area of the sector minus the area of the triangle. The area of the sector, so this is going from, so that's P down, so we've got this sort of thing going on here. We're looking at that angle, so we've 1 across P down. So that angle there, let's call that theta. So area of sector, that's angle theta. So we're going to have the total area of the circle. So we've got pi r squared. So it's this bit, isn't it? So pi p squared plus 1. That's the area of the whole circle multiplied by theta divide, well, 2 theta, because I've done half of the angle of the sector, divided by 2 pi. So that's the area of the sector. We can come back to theta. And then we have to take off the area of the triangle, which is going to be P times 1, P. Okay, so that's easy enough. Where theta, well, actually tan theta is going to be opposite over adjacent, so that is 1 over P. So theta equals tan to the minus 1 1 over p. Right, we just got to put it all in now. So we've got pi over 6. Oh, which they do have here. I haven't really paid much attention. Oh, and we got the p. Oh, we got everything there. It's done, isn't it? That 2 cancels with that. That pi cancels with that. So we've got pi over 6 is equal to p squared plus 1 tan to the minus 1 over p minus p. Right, that drops out really easily. Once you've done the picture and spotted that these areas have got to be the same, then the actual geometry bit of it isn't that tough. That was a lovely question. I really, really like that one. But again, I like geometry questions. I like circle questions, so it's not a surprise. But that was really well put together, I think, all in all. Interesting points right from the start. Even the second part of the question wasn't a trivial bit. You had to make little insights as you went along, but they didn't overload it as just making it a slog on the algebra or anything. They kept it as actually being able to visualize the geometry rather than anything else. So yeah, that was a top-rate question.